Hello and welcome to this episode of Claranet Cybersecurity TV. My name is Alexi Bitsios and I'm a senior penetration tester with Claranet's Security Business Unit, formerly known as SEC1. In this episode of CCS TV, I'll be going over the OWASP Top 10's A1 injection entry, and in doing so, I'll briefly go over what is the OWASP Top 10. Then I'll be looking at the intricacies of injection attacks, moving on to how to identify these vulnerabilities using a variety of methods, and finally I'll wrap up with some basic prevention and remediation suggestions. So OWASP stands for the Open Web Application Security Project, and they believe in providing general cybersecurity advice for everyone, and that it should be completely free and freely available. The OWASP Top 10 list is a list of the most critical web application security risks as they see it, and they like to call this an awareness document. As the name suggests, these are 10 vulnerabilities or vulnerability categories, which OWASP has determined to be potentially the most dangerous, the most damaging, and the most common found across web applications. As you can see, there are 10 items in this list, which will create one episode per entry, and today I'll be looking at A1 injection. Now, injection attacks can occur in a variety of technologies. The most common, which I'll be basing this presentation upon, is SQL injection. You can also have LDAP, operating system, so for example, remote code execution, XPath, NoSQL, and so on. And looking at a very high level, these vulnerabilities occur when untrusted user-controlled data is sent to an interpreter as part of a command and/or query. Now, this leads to the interpreter executing unintended commands and can lead to a lot of unintended consequences, such as the destruction of data, authentication bypass, the exfiltration of large amounts of potentially sensitive data, and so on. So looking at how you can identify these vulnerabilities through a black box perspective. There are two main ways in which you can achieve this. The first is using automated tools, and the second is to manually crawl the web application to identify parameters and run through the process manually. With an automated tool, such as SQL Map, for example, the tool you'll provide some basic information to the tool, such as a URL, potentially an HTTP request, and this tool will then send a large number of payloads to the available input parameters. If one of the parameters is vulnerable to some form of injection attack, the tool will understand this from the server response, and then using that specific payload format, it will then proceed to execute whatever it is that you may be trying to do. So, for example, extract a specific table from a database. These also tend to be able to apply common bypass techniques, as these tools, generally speaking, have been around for a while. They do have a large number of supported formats and bypasses. However, due to the amount of traffic that they generate, with some very easily identifiable aspects, they're rather easy to spot and defend against if you're using some technologies such as a WAF or web application firewall, for example. Now, the manual process is a bit more time-consuming. However, it does cause a lot less noise, and it's a much more targeted attack. Generally speaking, the way you'll go about this is you can proxy your web traffic through a tool such as Burp Suite, for example, and simply browse the web application. Once you've got a good coverage over the functionality and pages provided by the web application, an attacker will then review the potential input points, so the parameters that they have access to, and from there manually enter payloads to identify potential vulnerabilities, and then once one has been identified, they will work with that in order to achieve their objective. From a white box perspective, so with access to the source code, the underlying source code for the web application, the first and foremost thing that needs to be looked at is when user-supplied data is not sanitized, validated, or filtered, and then is then passed directly into a command or query. You can also look for dynamic non-parameterized queries without interpreter-specific escaping. I know that's a mouthful. We'll be looking over that in the remediation steps in a bit more detail. And finally, when unsanitized data is inserted into dynamic SQL queries containing both structure and data. Again, we'll be looking at that in a bit more detail at a later stage. Let's look at some examples now so that we can all get on the same page. Here we'll be looking at some authentication bypass, some very simple authentication bypasses using both SQL and LDAP. So the query we see here at the top is a very basic SQL query, which is simply checking that a a user exists with a provided username and password. This is written in PHP, and then you could run for example, a function to check how many records are returned for this specific query. If it is greater than 0 or equal to specifically 1, then this user exists and the authentication process should continue. If we were to add some traditional credentials here, so for example, username of Claranet and a password of super secure, if this user existed in the database, then the user would be authenticated. However, if we were to pass the strings in the user and pass variables shown on the screen here, we need to be careful to make sure that the single quotes were in plain text. This is simply a formatting issue, and I apologize for that. However, each of these SQL injection payloads will allow for a true statement to be returned. That is to say, select ID from users where the user or username is equal to nothing or an empty string, or A is equal to A. And the same thing for the password field. Now, as A is always equal to A, this will show a true, this will return a true result. And unless some much more intricate protections have been put in place, this will lead to authentication bypass, as this overall query will return a value of true rather than false. And in this instance, the attacker does not know a set of valid credentials. Usually, in this case, this would return the ID of the first valid user, and they would potentially be logged into an administrative account. As generally speaking, the first user within a database is going to be the administrative one. Now, looking at LDAP again, it's a very similar process. We log in with an LDAP query here, where the user can pass a username and password variable for each, and if that user exists, the authentication process continues on. Now here we can add a slightly more complex injection payload here, and essentially we'll say if this user exists, which as we're using the wildcard asterisk here, it will always exist, and then we can add a password of anything as it does not play a role within this query. This will also lead to authentication bypass, and as previously mentioned, unless there are some much more intricate processes running in the background. So let's look at some prevention and remediation steps that can be taken. First and foremost, it's possible to implement a web application firewall, which can identify potentially malicious requests, which may contain SQL injection payloads or general query injection payloads. However, this is a quick fix that may prevent the issue from occurring, but this does not remediate the underlying issues. And if an attacker or a threat actor is able to find a bypass for the web application firewall, they will be able to extract or inject their malicious payload and potentially execute malicious commands. So you can also move to an API-based solution, or say a framework. These generally avoid the direct use of interpreters altogether. And generally speaking, again, they will implement a parameterized solution. You can also convert your solution to an ORM implementation, which generally speaking also prevents these issues from occurring. Now, I've talked about parameterized queries a lot, and one of the best ways to avoid these vulnerabilities from occurring is to use them. A parameterized query will set up the structure for a, say, SQL query first, and then it will add the user data in a way which it cannot affect the structure of the query. This means that whatever data is passed into the parameterized query cannot be used to break out of that and execute extra commands or query functions. This is a very good way to protect against these kinds of vulnerabilities. However, it is important that developers understand how these work, as there are still ways in which these vulnerabilities can appear in parameterized queries. Another great way of preventing injection attacks is to use server-side whitelists for allowed characters. That is to say, if you have an input that only expects an integer, then you can put a whitelist there which only accepts characters 0 to 9. If you are looking to add a name, for example, you can do lowercase and uppercase A to Z, and then maybe a dash for some of the more interesting names out there. Apply interpreter-specific special character escaping. So as we saw in the SQL injection example, the single quote was dangerous, and generally speaking, you also wanted to escape some other characters such as double quotes. By escaping these through, generally speaking, the use of a backslash before the character, it's not taken literally, and it's rather saying that we want this to be included in the query, so don't break the structure of it. Finally, and this is more of a defense in depth tactic to use, you can implement a limit statement within your query to minimize the number of records to be returned. This will hinder an attacker's ability to exfiltrate large amounts of data with single queries, and the number of requests that need to be sent to the server will increase hugely. Thank you very much for listening and watching. I hope that this video was useful, and be on the lookout for the next installment of CCS TV, where we'll be going over the other OWASP top 10 entries. Thank you.